Hello everyone, Lucky here. Today we're taking a look at electrodynamic ion traps, what they are, how they work, and how you can build one yourself for around $100. Ion traps are devices that let you hold tiny charged particles in place without touching them. This is useful for things like quantum computers, where you might need to hold a single ion in place without disturbing its quantum state, or in a mass spectrometer, where you can determine how much of a given type of ion is present in a sample by only trapping ions with the correct charge-to-mass ratio. I got interested in ion traps while looking for a way to store antimatter, which is famous for annihilating in a burst of gamma rays if it ever touches normal matter. Unfortunately, trapping antimatter this way is really hard, for reasons we'll see shortly, so we'll just stick to trapping macroscopic particles for this video. So how do you trap a charged particle with electric fields? The first thing you might think of to try is to just put the particle in a metal box charged up with charges of the same sign. Since like charges repel, the particle should stay in the center of the box, right? Unfortunately, it's not that simple. Let's take a look at the electric field created by our charged up box. The electric field is represented by a bunch of vectors.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
Oh yeah! Excuse me. Anyways, these vectors show the direction and magnitude of the acceleration a charged particle would feel at that point in space. When we add up the electric fields from all the charged particles on the surface of the box, they end up canceling out everywhere inside, which means nothing would stop the particle from drifting over to one of the walls. If we want to trap our charged particle, we'll need to put it somewhere where all the nearby electric field lines point inwards. That way, no matter which way the particle wanders, it will always get pushed back the other way. Maxwell's equations tell us that electric field lines can only start or end at a charge, so the only way to make all the electric field lines point inwards is to put some negative charges where we're trying to trap our charged particle. Well, that's just great. We set out to trap a charged particle using electric fields so we wouldn't have to touch it, and now you're telling me the only way to do it is to have it touch another charge? There is one glimmer of hope on the horizon, though. We only need the electric field to be pointing inward all around the particle if we want to trap the particle without ever changing the electric field. If we had some electric field that could respond to the particle's motion and counteract it, then we could keep the particle trapped without it touching anything. This is where the electrodynamic ion trap comes in. One of the simplest types of trap is just a ring electrode with an oscillating voltage applied to it. Here is what the electric field looks like in a cross-sectional view. We can see that the electric field is 0 in the center of the ring, which is where we can trap our charged particle. Let's take a look at what happens if the particle gets bumped out of the center and starts moving towards the electrode. Since the electric field is stronger closer to the electrode, the pushes away from the electrode are a bit stronger than the pulls towards it, so eventually the particle gets pushed back to the center. The same thing happens if it gets perturbed straight up or down. But what if it starts moving diagonally? Now the electric field is pointing perpendicular to the center, and it looks like there's no way the field could push the particle back towards the center. Fortunately, the electric field is curved. That way, the forces at either end of the oscillation don't quite cancel each other out, eventually pushing the particle back to the center. To make the trapping stable, the electric field needs to be strong enough to counteract any random perturbations the particle would feel, which usually requires high voltage. The frequency of the oscillating field also matters, since if the field oscillates too slowly, the particle would get ejected from the trap before the electric field even oscillates once. This is why we can trap macroscopic particles with our 60 Hz AC power coming from the wall, but we would need megahertz frequencies to trap individual ions, since they feel a much larger acceleration in an electric field. Finally, we need a little bit of damping from forces like air drag to help the particles lose their kinetic energy and settle down in the center of the trap. Okay, enough theory. Let's build one for real. I used a 120 volt to 5 kilovolt transformer to create the high voltage needed for the trap. It oscillates at 60 Hz, since that's the frequency of the AC wall power in the US. I'm using a variac so that I can easily turn it on and off and decrease the voltage if I want to, but this part isn't strictly necessary. The output of the transformer is connected to a 10 megaohm, 1 watt high voltage resistor, which then connects to the electrode. The resistor is there to limit the current I could get shocked with if I accidentally touched the electrode. The electrode is a removable piece of wire held in place by a plastic tube. I colored it with black Sharpie so it wouldn't be so bright on camera. This whole setup is enclosed inside a cardboard box because even tiny air currents can disturb the trapped particles. I've got a viewing window for my camera, a little door for inserting particles, and a laser to illuminate the particles. This is a homemade laser with a diode I got out of a DVD player, but a regular old laser pointer would also work. I'm powering it with an Arduino, which strobes it on and off at around 59 Hz. This way, every time the laser turns on, the particle is in almost the same point in its oscillation as it was last time. So it looks like the particle is moving slowly enough to see, even though it's actually vibrating back and forth 60 times a second. I use the bulb of a pipette rubbed with a paper towel to generate the static charge, and then touch it to this dish of aluminum powder to create and pick up some charged aluminum particles. I'm using 30 micron aluminum powder, although pretty much everything I tried worked, including Lycopodium moss spores, carbon black powder, and even dust from around the lab. I get the particles into the trap by scraping the pipette on the electrode and then pulling it out quickly. If I don't pull it out quickly, the charge on the pipette can push the particles out of the trap. You can see that the particles form a sort of pulsating dandelion shape because they're all attracted to the center of the trap, but also get repelled by each other. This shape is called a Coulomb crystal, and it's not always stable. You can sometimes see the particles fighting for their places like angry squirrels, which is called an extended orbit. If I turn down the voltage, the Coulomb crystal expands, and the particles with less charge will get ejected from the trap. It turns out that a lot of different electrode shapes work. I got the best results with a circle around 1 centimeter in diameter. Turning the circle sideways, you can see the three-dimensional structure of the orbits. Here's what a diamond electrode looks like. And here's a circle with a larger diameter. In total, this project cost me around $100, and I put links to some of the parts I used in the description below, along with the paper I based my design on. It's a shame these traps don't work well for storing antimatter. I would need to use megahertz or gigahertz frequencies in an ultra-high vacuum to trap antiparticles for any reasonable length of time, not to mention the difficulties with slowing them down from relativistic velocities to get them into the trap in the first place. On the other hand, this means it's time for me to start messing around with magnetic traps, like the kind used in fusion reactors, if I want to trap antimatter. I hope you enjoyed this video. Like and subscribe if you'd like to see more projects like this one. See you later!